across time and across geographical and ecological regions are fascinating. And we are ultimately interested in understanding the processes that generate these patterns. However, at macroevolutionary timescales, we can rely on data from the fossil record or on species number or molecular ages obtained on molecular ages and analyzed with mathematical modeling to discover that different types of diversification models can explain these distribution patterns, and that these models predict either that diversification is limited and decreasing through time, or that diversification is unlimited and increasing through time. One way to evaluate these incongruent conclusions is the use of simulations and compare expected and observed summary statistics to try to determine which model can explain the data best. One of the most popular of these summary statistics is the relationship between age and richness. And recently, in 2012, it has been pointed out that phylogenetic structure can badly bias this relationship. And even more recently, in 2013, it was pointed out that some forms of taxonomic categorization, depending on the type of age we use for estimating this relationship, either crown age here in green or stem age here in brown, can also bias the relationship. So in this work, we aim to reassess the relationship between age and richness in extant higher taxa in nature, and while taking into account all these possible sources of bias, such as phylogenetic structure and taxonomic structure, and also determine if more commonly used taxonomic frameworks, such as the hierarchical one we almost always use, can affect this relationship, and also determine if it can vary with the type of age, crown or stem, and if it can vary across biological systems. So we compiled data on ages within these 6 different biological systems, and these ages were obtained from molecular dating studies. We chose trees with almost complete sampling within at least 2 different taxonomic ranks, so we could evaluate the relationship with this hierarchical taxonomic structure. And then we obtained species number counts from each of these biological systems at the different taxonomic ranks, and then analyzed this data with macroevolutionary comparative analysis with independent contrast, which corrects for phylogenetic structure and is especially designed to analyze species richness contrasts. So here I am showing the main results from this analysis within 3 taxonomic ranks in mammals, and here in green I am showing the relationship estimated using crown age and the relationship between richness and stem age. And we can see that with crown age it is always positive, and with stem age it is always negative, and that the relationship decreases with taxonomic rank. And these 2 patterns are also observed in taxonomic ranks from birds. So we have positive crown age, relationships between richness and crown age, and negative relationship between richness and stem age, decreasing. And here with data from squamate reptiles, we have also the same pattern, but with the exception that we obtain a positive data point using stem age, but only using a taxonomic rank that is very inclusive, which is infra-order. and we get the same with angiosperm data. And the only outlier is the correlations computed for the taxonomic ranks of amphibians, which show no change neither among taxonomic rank nor between crown age or stem age. So to evaluate these patterns, we developed a simulation approach that includes origination rate. So we, as an evolutionary model, we use a two-state product process that draws branch lengths from an exponential distribution with this parameter that includes speciation rate, extinction rate, and origination rate. And this graph shows how adding the origination rate parameter slightly changes the distribution. Here I am showing you when the origination rate is not included. And it's important to mention that this origination rate is not equivalent to the speciation event, so there is no branching event. It's just the appearance of a characteristic or a trait that allow us to categorize all the lineages that have this trait within the same group. So once we have our tree, we use the origination events here to produce the taxonomical model, and the first origination events to appear would define groups from a first rank, the most inclusive groups, and then the next events to occur would define groups nested within the first rank groups. And we can also have many origination events occurring in the same branch. However, this does not affect the taxonomic model, and we force the groups to be monophyletic. And well, then we use this framework to perform simulations with three different diversification models: one of constant rates, one with diversity-dependent rates, and one with rates that can vary among lineages. Then we evaluated three different origination regimes. One where origination rate can be is lower than speciation rate, then where it is equal to speciation rate, and then where it is higher than speciation rate. And then to evaluate the effect of extinction, we considered three different extinction regimes with no turnover, moderate turnover, and high or complete turnover, where extinction is equal to speciation. So here I am showing you the results for the constant rate models and all the possible combinations with origination rate and extinction rate. And I am going to focus first on the effect of origination in the estimates of the correlation between age and richness. The x-axis shows the simulated taxonomic ranks from the most inclusive to the less inclusives to the left. And in green again the relationship estimated with crown age, and in brown with stem age. And here to facilitate the comparison, I am connecting the modes on the distributions across taxonomic ranks. And we can see that as origination increases down, both correlations estimated with crown age or stem age decrease with taxonomic rank. And this is what we observe in most of our empiric trends. And now focusing on extinction rate, I am again connecting the modes of the distributions. And the second pattern we observe is that as extinction increases, here to the right, the stem correlations can take positive values, but only at highly inclusive taxonomic levels, which are equivalent to infraorder or superfamily, and the relationship obtained with the crown age can become more positive. And we, evaluating a model with a diversity-dependent rates, we also recover these two patterns, and we also observed that no correlation using crown age can be obtained when extinction is low or moderate, and this is similar to what we obtain with amphibians. And in the model of variable rates among lineages, we also recovered these two patterns, and we, with the exception that when we allow diversification rate to be negative, we obtained the most negative values of the correlation estimated with stem aging, as we observed in mammals. So to conclude, I guess we can say that the relationship between age and richness do vary with the biological system, and that this may depend on some characteristics of the organisms, or maybe the total time that the group has been diversifying, and also that the relationship between age and richness varies with taxonomic rank and with the type of age, and that the difference between stem and crown correlations cannot be explained with the diversification process, and neither with extinction. And maybe this can be explained by the hierarchical taxonomic structure we use. And we also suggest that maybe other factors that are also studied using correlations may be subject to the same taxonomic biases as we see here with age. And finally, we encourage the inclusion of origination rates in models to study diversification, since they may be important in our conclusions. So, thank you very much to my co-authors, my universities, and to all of you